Hopefully smaller topics. This was one of our lead slides on dealing with the different forms of spectroscopy and how we go through and prove things. So we've got UVvis, which you've technically already learned about and used in Gen Chem. We've got IR, which we discussed a little bit earlier in the semester. And then mass spec and NMR. Mass spec and NMR we've now covered, so we really just have the UVvis and IR left. Electromagnetic spectrum, it's energy. Depending on which energy range you're in, you cause different molecular effects. So X-rays and UV or deep UV ionize. So what's happening is you're hitting your particle or you're hitting your molecule and it ejects an electron. When would we do that? Mass spec. That's the whole point of mass spec, is to ionize it. When we get into the near UV and the visible, we're now talking about still exciting electrons, but this time not enough to eject them from the molecule. Okay, so that's looking at the electronic transitions. Okay, this would be jumping between orbitals. Atomic line spectra, UVvis spectroscopy. Okay, so now what we're going to do is shift and look at molecular orbitals instead of atomic orbitals, and how that translates for our electronic transitions. You then get IR, which is molecular vibrations, still moving electrons, just not a whole lot. Okay? So now your bonds vibrate. Microwave, you get rotational motions, and then all the way down into radio, you get your nuclear spin. Okay? So all our different forms of spectroscopy somehow deal with the electromagnetic spectrum. It's just what are they actually doing, and how are we observing that? So in our IR range, you're typically looking about 4,000 to 400 inverse centimeters. You don't need to stress necessarily where that inverse centimeters is coming from, okay? But we've got all that Planck's constant stuff that everybody loved from 151. So there it is, ta-da! That's about it, okay? The big relationships you need to understand is your energy and your frequency, and in particular, actually your energy and your wave numbers. Okay, why wave numbers? Guess what a wave number is? Inverse centimeters. Okay? So your IR, that bottom line, x-axis, is written in wave numbers. Okay? Those values that we're seeing, the larger that value, we're seeing a larger energy associated with causing that bond to vibrate. Okay? And that's where it's coming from. So we could look at quantification behind all of these. One of the things that we'll notice is the stronger the bond, the higher the frequency, right? Which makes sense. Our frequency is looking at our wave numbers effectively. So a higher energy is necessary to cause that bond to vibrate, okay? And that's about it. You can see some relationships with atomic mass. If you really wanted to dig into that, I don't think I ask anything about it, okay? So I wouldn't stress a whole lot there. Okay, but what I do want you to recognize that it is a bond. And all a bond really is a spring. You've got two weights on the end of that spring. How much energy do you have to put in to cause it to vibrate? That's about it. Okay? There are tons of vibrational modes that you can go through. Okay? You can look up all sorts of fun, goofy videos, probably of instructors doing weird jazzercise exercises, okay, where they're trying to show you the different vibrations. Okay? So if my hand was an atom and my body was the other atom, the vibration, okay, causing that bond to oscillate back and forth. You can see bending modes as I then punch people in the head and stand back. Okay? You can see some bending modes of that. If you add in another bond, okay, you can get symmetric stretching, right? Starting to see where jazzercise comes in. Asymmetric stretching, scissoring actions. Okay? All of those are vibrational modes, and those vibrational modes will appear in your IR spectra. Okay? Most of those tend to fall deep into the fingerprint region, and so we tend to not stress about them as much. And actually, I'm going to double back to that. Let's look really simple right here. What happens to the frequency of those vibrations? It gets higher. Okay? What also happened to the bond strength?
It's stronger.
It gets stronger as we go from single to double to triple. Okay, we're getting respectively, okay, a stronger attraction between those atoms, and that's causing the frequency to increase. Okay? Are there other things that can cause bond frequencies to change their energy? What could cause that purple pi bond to change its energy? What it's connected to. What happens if, say, I put a nitrogen next to it? What could that nitrogen do? Resonance. If it shares electrons in, what would happen to that carbon? It would exceed the octet. So what happens? Those electrons shuttle up. And now what's the result? What happened to that original pi bond? It's now a sigma bond. So what did we do to it? We weakened it. Because it is now a weaker bond, what happens to the frequency with which that carbonyl appears? It decreases. Okay? And we can see this trend pop up. Whenever we weaken a pi bond, that frequency appears at lower and lower wave numbers. Okay? So it's kind of a neat, subtle observation that you can sometimes see questions about. Yes? Electronegativity is largely going to be changing the bond strength. That's changing the atom that's connected to it, and that's going to be causing the energy of that bond. Okay. The other thing that comes out is bonds dipoles. Nearly everything in IR has to do with an asymmetry in the molecule. That's what you're detecting, is that asymmetry in how the electrons are being dispersed, and that's what we detect. Okay? So if we think about what we remember, because we've been reading the book, the carbonyl is a very intense stretch, right? That is a very intense stretch that shows up where? Okay, about 1,700 inverse centimeters. Okay, and it tends to be, if you look at how it's referenced as a strong, intense peak. Right? If we instead move to a CH bond, where does the CH show up? Okay, depends on the hybridization of the carbon, which is changing that bond characteristic. Okay, but as we change that energy of that carbon, we're looking somewhere around that 3,000 range. Okay, how intense is it? Okay, it's not as intense, and if we look at it, we're usually referencing, say, medium. Okay, sometimes you'll see strong in there. Sometimes you'll even see weak, which is pretty awesome. Don't you love that descriptor? This bond can show up as either a weak, a medium, or strong, intense peak. Thank you. So you're saying it just exists. That's about it. Yes. Okay. Why is the carbonyl showing up as strong, but the CH showing at varying abilities? It has actually nothing to do with the double bond. It's not quite electronegativity either. Okay. It's similar to that. It's kind of what this slide is representing. We're talking about symmetry. Okay. The carbon-oxygen double bond has a large difference in electronegativity, which means we have a very asymmetric bond. So electronegativity contributes, but it's not the be-all, end-all of it. Okay? That's an asymmetric bond, which means when I hit it with energy, I see a very strong absorption. When it's a symmetric bond, carbon to hydrogen, I don't see as much of an absorption. Okay? In IR, it's all about that asymmetry, that dipole moment. So the larger the dipole moment, the more intense the signal. And that's where we're referring to bonds as being IR active. Most of the bonds you have studied have been IR active. Why? Because they show up. That's why we look at them. Okay? It is also important to acknowledge that there are some IR inactive bonds that have zero dipole moment. How would we get zero dipole moment? It's got to be the same on each side of it. Okay? So we heard reference real quietly to a carbon-carbon. Okay? That could be an example. The problem with carbon to carbon, It's connected to 4 other things, wedges and dashes, all that fun jazz, right? Okay. So that's going to make that a little bit more complicated to look at. But it is true. The carbon-to-carbon can sometimes disappear. It's also not analytically useful for us because this was an organic chemistry class. That might be an important piece of information to remember. There's lots of carbons. Okay? You are probably going to see a carbon-to-carbon single bond somewhere in your structure. It's not very analytically useful. Virtually everything we're looking at has carbon-to-carbon single bonds. Right? So what we want to do is level that up a little bit. We could go through and look at the carbon-to-carbon double bond. Okay? That simplifies things a little bit, and we could now, because now we're trigonal planar, right? And we could now start to see if that signal starts to weaken out. Okay? That's also one that tends to show up fairly intensely, though. Okay? So let's push it all the way. Let's move to the triple bond. Okay? The triple bond is our classic example of this dipole moment. Okay? For it to have a 0 dipole moment, what does that carbon need to be connected to?
Or another carbon.
Another carbon. Now they have equal electronegativities. Because they have equal electronegativities, there would be 0 dipole moment. Except because this is an organic chemistry class, we've probably thrown a bunch of other stuff in there, right? Okay. Like maybe some other carbons or maybe a hydrogen. Okay. Does that generate a dipole moment now? This carbon is different enough than that hydrogen, both in mass and electronegativity, that we do see a dipole moment, and we will see that carbon triple bond show up. But what happens if I turn that hydrogen into a carbon? Okay. Now it is exceptionally symmetric. So what happens to the triple bond? It disappears. You actually won't see it in your IR spectrum. Okay. It is the cleanest and easiest to see this IR inactive system, okay, when we're looking at that triple bond because it's linear. It's really easy to establish that visually with that 180-degree complete polar opposite of each other. Okay? So when you're looking at kind of trick questions-ish, the triple bond is usually a red flag that you might be seeing something as IR inactive. Does that mean you don't expect to see a triple bond ever show up?
Because it could be IR active.
It could be IR active. How can we make that IR active? Make that an H. Okay, how else could I make it IR active? Could make it a nitrogen. Okay? That carbon-nitrogen triple bond is now exceptionally polar. You've got the electronegativity, the difference in nitrogen versus carbon. That bond shows up very, very intensely. Kind of make sense? Okay. So, symmetric triple bonds. Convenient. What do you see? Okay. So CH isn't a bad place to start. Okay. We should be more specific and quantify the hybridization of that carbon because we studied Unit 1 and we know more information. So put that information in there. Why do we know that is CHSP3 and not, say, CHSP2? You're looking at that 3000 line. For those people that have come to see me in office hours, I've pulled out a piece of paper. You've got an exam with multiple pages. Tear a sheet off and line up the bottom of that along the bottom of your axis. And then slide that over to the 3000. If you see a peak, then it's probably CHSP2. If you don't actually see the peak, then it's probably CHSP3. That is how refined that line is. Okay? So a peak at 30,000, I was going to do 3000, but 3010, just 10 units off of that 3000 line is probably a CHSP2. Okay? So being able to identify and find that relatively quickly is a useful thing. Okay? What else do you see? That's about it. Okay? That 1500 line is usually where I draw my limits, and unless I'm forced to, I will avoid looking at this whole range. Avoid is spelled with an A. Okay? And not because it's not useful. There's a lot of information in there, and you may be asked to dig into that, particularly when it comes to lab. Okay? But for the lecture and for most exams, you aren't expected to dig in there. Okay? Why? So much stuff happens in there, it's not worth your time. Okay? Which means you need to be spending most of your time this direction. Okay? You'll notice 1500 is a little bit higher than most textbooks reference. They usually say 1400. My argument is pretty much from 16 to 1400 is dicey, because there's all sorts of stuff that can fall in that range, and I get a little uncomfortable assigning anything at 1600 even. Okay? That is my personal preference. I've done fairly well by kind of ignoring that range, so I would argue you could do fairly well by doing that same thing. Okay? Just be careful analyzing in there. Yes?
Does the missing bits at like 1700 and below, does that?
Interesting question. If we take a look up at the top there, you see this big white gaping hole. Yeah? That is not something being deleted from the spectrum that I'm aware of. That's an artifact of the system of where this spectra was found. Okay? And for whatever reason, they didn't complete the spectra through there. Okay? So don't be like, oh, there's a blank space, so that must mean there's a peak there. No, if you don't see a peak, there's not a peak. Okay? Don't start adding things in there. Okay? I will say that there are cases where there is missing information that I think would be useful, and I will draw stuff in there. Why was it missing to begin with? Why was it missing to begin with? It was probably an IR inactive bond. So you're seeing my crude attempt at drawing something in there to help give you that hint that there is something there, that maybe there's something weird going on within it. Make sense? Okay. With that, we're probably going to see mass spec HNMR and carbon NMR, so I'm going to skip over those for the moment. There's our major regions of the IR spectrum, okay, color-coded out. Every textbook has some version of this. Okay. Again, I would sit in about 1600 up that you should be evaluating. Okay. So what this does is it just summarizes those major regions, okay, and what you could see within them. Okay. There are other ways to represent it. I've literally been in classes where this is what they give out. They're like, here, you can use this. For what? Keep you warm at night when you light it on fire. This is how IR was effectively done to begin with. Okay, we fired IR light at something and noticed this weird absorption. So we started subtly changing the structure and saying, well, the existence of a new peak meant this. Okay? And the more we learned about bonding, the more we could quantify where everything shows up. If we take just a look at that bottom line, just so I can say that you've seen this, we're looking at amines here. If we look at this bottom one right here, they're saying you could expect a medium intensity peak somewhere in that red range and a medium intensity peak somewhere in that blue range. Okay? Why? If it's a primary amine, you have an NH bond. How many NH bonds do you have? Two. If it's a primary amine, it's only connected to one other carbon. It turns out for a primary amine, you expect 2 peaks in the NH region. That's how they're showing them. Right? As we continue along, you'll notice a bunch of dots. What are those dots representing? Nothing. Okay? Nothing of relevant interpretation until we encounter another line. Okay? We'll call that a purple line. There's an S, I believe, underneath that. So they're saying there's a strong peak there. Okay? What are they saying that's in reference to? They aren't. They aren't at all telling you what it's in reference to. But if we look back along that dotted line, what do you see in there? They're seeing a little structural piece of information. That structural information is to help you kind of elucidate what the rest of those signals would be. Like, that's how you use it? Yes, it sucks. It's awful, but you can use it. Okay? I've told a bunch of people this, but when I learned IR, this is what I went through and studied until somebody was like, there's better spectra to look at. Okay? Wish they told me that first, and I wouldn't have looked at this. Okay? So it is out there. You can find more information in IR, but it's significantly more difficult to pull that information out of IR than it is out of any other form of spectroscopy. So what should you be committing to memory? Not that. Good to know. See, you're welcome. Okay. First off, IR gives you information about bonds. Does it tell you how many bonds? No, it just says a bond that matches that description exists in this molecule. Okay, that's it. Okay, it doesn't say there's 2 or 3 or 4, any of that. It just says there's at least one. So what are the ranges that you should memorize? You should know what an OH looks like, that it falls from the 33 to 3500, and it's usually intense and broad. Okay? That is now useful information so that when you look at an OH or a spectra and you see something there that matches that characteristic, you know you have that bond class. Okay? So these 6 things should be memorized. Notice there's the triple bond. What did I say the triple bond was to?
We don't know.
It doesn't matter. It could be carbon or nitrogen. It's still going to show up about 2150. Okay, what else shows up in the 2150 range?
I don't know, it's my own list.
Nothing. It's a dead zone in the IR. The only thing that shows up there is a triple bond. So if you're looking at a spectrum, you're like, why is there a weird thing here? Triple bond. Okay? So those are your general ranges that will cover you for probably 60 to 70% of the questions that you will see. Okay? If you want to do better than 60%, then I would argue you need another 6. Okay? These other 6 add a little bit more detail. I notice we've got the OH showing up again. This time, the numbers are different. Why are they different? The OH is next to a carbonyl. Why did that change things? We had the OH just near a carbon versus the OH near what is the difference between those two structures? Okay, I heard one. This is a carboxylic acid. Okay, if it's a carboxylic acid, what does that mean about that OH bond?
It's likely to break.
It's likely to break, meaning that bond is weak. What happens if your bond gets weaker to the energy? It lowers. What happens to your wave numbers? It decreases. There's a direct representation of that right here with the OH. You go from 3,300 to about 3,000. Right? The problem with this OH is that a bunch of other stuff show up in that range. Yeah, so it usually turns your IR into a giant mess. Okay? So if you look at an IR and you're like, God, that looks ugly, it's probably because of an OH from a carboxylic acid. Okay? If you look at them and you think they're all ugly, well, keep looking. Find nuances. Okay? Find the internal beauty. NH, 2 peaks. Primary, 1 peak. Fudge. That's called copy-paste. Secondary. Okay? So if you only see 1 peak, that's just an NH. If you see 2 peaks, that was a NH2. Okay? So again, having slightly more information about what they look like can allow you to draw conclusions faster. The CH from an SP, I honestly haven't bothered to memorize, and I'm shocked that it shows up that high, but it does. Okay? Why would it show up higher?
Higher energy.
Why is it higher in energy?
The
Okay. Dipole is bigger. Remember this looking at our energy. Okay, the dipole has to do with intensity, not where it shows up. The carbon's triple bonded to the hydrogen? Okay, so why is that causing it to shift to a higher energy? What happened to the overlap between the carbon and the hydrogen? You have less p orbital in that s character, or in that s orbital, okay, which means it's less elongated, which means what happens to the bond overlap or the orbital overlap between the carbon and the hydrogen? it increased. Okay, we get a stronger overlap, which means a higher energy bond, larger wave numbers. So again, we can see those references come out. Okay, you got the CH from an aldehyde, so that's referencing that one. Your carbon-carbon double bond, 1650 is our alkenes. The 1600 and 1450 is when it's an aromatic. Okay, so these are subtle changes to the previous slide, okay, that you should be using to try and nail down those types of bonds. Make sense? Okay. In your general interpretation, it should be fast. You should be able to look at it and just say, that's what I see. So in this case, this spectra, this is typically how they look actually in textbooks. Okay. You've got a bunch of labeling on there. What's the labeling that I would expect you to do? And that's it. There's a bunch of other stuff there. You aren't expected to know that. Are not. Okay? Kind of, sort of? Okay. So, what do you see? And that would be it. Okay? What do you see? What do you see? And there's a little, I don't care. Okay? Why is this one now all of a sudden a CHSP2, not just CHSP3? Okay? That peak, you're like, oh, that's greater than 3,000. Just barely. Okay? Notice how just a subtle change in that spectra, without actually putting up that line, people were jumping on that being a CHSP2. C double bond C, that's at 1600, that says 15. Okay, and we have that. Those are probably both tip-offs that we're looking at an aromatic. Isn't what below 1500? Is that carbon-carbon showing up below 1500? Yes, it's the combination of both of those that would cause me to evaluate that. Oh, and that would be all of them. Nope, there's no one. What do you see? So I heard a CHSP2. $16.50. I heard people saying carbonyl, and I heard people saying carbon-carbon double bond. Ultimately, that's a little bit higher than 1650. That's probably looking at your 1670, which means it's kind of high for a carbon-carbon double bond. It's also kind of low for a carbonyl. Okay, so you could question mark that. And to show your work, you're acknowledging that you have weaknesses. That's okay. I will look at it and evaluate it. Okay. The CHSP2, there is that little side peak there. That is possible. I would pull out a piece of paper to line that up because I doubt I can do a straight line remotely close to that distance. Oh, really? Close enough. Okay. It's kind of on that line, so what you might do is even throw a question mark on that. Does that make sense? In a show your work, that's the level of detail I would expect for an IR. If you found out more information, you could double back and you could cross it out. Don't erase things. Okay? By erasing that, you're saying that that work was entirely wrong. If it was entirely wrong, why did you write it down? Okay? So spend some time to write that down. On a multiple choice, what you would now be fishing for is seeing what is in your structural answers. So you got 4 answer choices. Which one of them lines up best? Make sense? Okay. So, that's IR. UVvis. Okay, these are electronic transitions. We're causing electrons to jump from one orbital to the next. Okay? This is Beer-Lambert Law. You can do all sorts of math and stuff if you want to. Okay? What you will hear reference to is a couple different things. Number one, knowing what your axes are. Okay? What is that little tilde thing? It's not a tilde, it's a lambda. Lambda. I think that's right. Okay, that's our Greek letter for wavelength. Okay, because we've been talking about it. What does that mean for energy? How is wavelength related to energy?
The closer your wavelengths are together, the more energy.
The closer your wavelengths are to each other, the higher energy. So what you're referencing then is peak distance, not the closer your wavelengths are. So I know what you're saying. So if your peak distance gets closer, your wavelengths get higher. Wavelength is distance from peak to peak. So if your peaks get closer, your wavelength gets shorter and your energy gets higher, which means they are inversely related. So that alpha is for proportional. Okay. So if I'm looking at this, I'm seeing a peak, lambda max. Lambda max is where did that molecule absorb the most light? Right? Or said another way, where did it absorb the most energy? It absorbed the most energy at a wavelength of 224 nanometers. That's where it absorbed most intensely. So what does that mean? That means in this molecule, there is a transition that equates to the energy at 224 nanometers. Okay? So if we think back to atomic spectra, energy 1, 2, 3, vaguely ringing bells? 5. When we're talking about, this would be a Bohr model. We're talking about electrons. If we cause the electron to jump from here to here, that corresponds to an energy level. Okay, that energy level, as far as UVvis, is now translated into a wavelength. That gap right now is large or small in comparison to this one.
Larger.
Which one's larger?
1 to 2.
1 to 2 is a larger energy or a smaller energy? It's a smaller energy, which means its wavelength is larger because of that inverse relationship. Right? So if I looked at the gap from 1 to 2, that wavelength is probably going to be, and I've got the inverses on this too, large wavelength, we're looking redder. Whereas the 1 to 3 would be purpler. Okay? Because it's a larger energy. Yes and no? Okay, so we heard a no, so let's walk through our rainbow. What are the colors in our rainbow?
Red, orange, yellow, green.
Which is the highest energy?
Red.
This is high energy. Red is low energy. What's a nice way to remember that? When you walk outside in the summer, you're afraid of the sun, right? For those being like, calm down. I'm not attacking your masculinity. You're afraid of the sun, so what do? You put on a shield to protect you. What was that shield? Sunscreen. What is sunscreen protecting you from? UV. UV, why are we protecting from UV? Because it is higher in energy. Which color light is closer to UV? V or R? Violet. That's our high energy end. The larger your jump, the more purple, the more violet. Okay? The smaller the jump, the more red. Okay? Where does this come into play with OChem? Well, in OChem, we're concerned about our electrons jumping. So if I looked at, heaven forbid, a molecular orbital diagram, okay, for butadiene, which electrons do you think I would be moving? the lowest energy. To move those to go up to here, how much energy do I need? I need a lot of energy. Okay? Is that lot of energy going to match the ultraviolet visible range? Visible range? Probably not. Our visible range is on the lower energy end of that spectrum, which means that jump is probably not what we're evaluating when we're looking at UV-vis. The jump we're looking at is taking these highest energy electrons. And where are we going to move them? We'll move directly up above. That gap is now the smallest gap. That's probably going to fall within the visible or ultraviolet range. Okay? So that jump is the most important jump for ultraviolet and visible spectroscopy. Okay? The other ones can still happen, they just aren't as important for us because they fall outside of our visible or our testing range. So we are taking electrons from this orbital and moving them to this orbital. Could that be confusing, going from this orbital to this orbital? Yeah, so it might be useful if we had names associated with these. So we could call them blue and purple, except you aren't taking colorful notes. Most of you aren't taking colorful notes. So we need a better name than blue and purple. What is different about the blue orbital versus the purple orbital versus the one even above it? Different energies, right? What else? It's occupied. Okay? So I could reference the blue one as being an occupied orbital moving to an unoccupied orbital. Cool. Except, isn't the red one also occupied? And I said I wasn't going to look at that one. So the blue one would be our highest occupied molecular orbital, and our purple one would be our lowest, but now unoccupied molecular orbital. And we get the acronyms LUMO and HOMO. So when we're talking about UV-vis, it's that HOMO-LUMO gap, okay? Which means a couple things for us. Okay? Number one, we would have to know what our molecular orbitals were. But since we did so great in that unit in chapter 1 or back in unit 1 with molecular orbitals, we're rock stars at that and we don't have to stress about it. Okay? Yay! Okay? The next part is it's not just that I have orbitals, it's that I know some are occupied, which means not only do I have to know the orbitals that are possible, I also have to know how many electrons went into said orbitals. Okay? Well, when I'm looking at this molecular orbital diagram, I'm actually referencing something very in particular. Okay? I'm not looking at all the molecular orbitals. How do we know we're not looking at all the molecular orbitals right now for this compound? This structure has a whole hell of a lot more than just 4 molecular orbitals. Remember, every bond contributes 2 molecular orbitals, a bonding and an antibonding. So why am I only looking at 4? Which of those molecular orbitals should we look at? You want a hint? The highest occupied are the most important. Well, the highest occupied mean they're going to be the highest energy electrons. Do I have a way of looking at this structure to very quickly determine which electrons are the highest energy? Why are the pi bonds the highest energy?
More electrons occupy the higher shells.
No, you just said they're the highest energy because they're the highest energy. More artfully, but that's what you said. Why are the pi bonds higher in energy? What are the other ones? Sigma bonds. What kind of orbitals make sigma bonds versus pi bonds? S versus p character. The s orbital is lower in energy than the p orbital. Because pi bonds are made up of only p orbitals, they are, by necessity, higher in energy. So when I'm looking at UV-vis spectroscopy, the thing that's most relevant for me are the pi electrons. I drew 4. Why did I draw 4? How many pi bonds do I have? 2. Good. Not 4, right? Why not 4? The other one's a sigma. So I have 2 pi bonds. For every bond, how many orbitals do I get? 2. One being bonding and one being anti-bonding. Okay? There's my 4 molecular orbitals. Okay? This is an interesting molecule because this isn't just 4 molecular orbitals. Whoops. Yep, no, that's what I wanted. Never mind. Organized like this. Okay? Why are they stacked instead of side by side?
Represents the energy levels.
This still represents energy levels. Is that a hand? No. Okay, just checking.
Excited versus ground.
It doesn't show the difference between the pi and the sigma antibonding.
Are we talking about sigma at all? Nope. There are no sigma orbitals. This is only the pi system we're evaluating. To show it side by side like this, we're saying here's 1 pi bond, pi 1, and here's pi bond 2. 2 electrons in each, right? As opposed to the other system on the right-hand side.
Which ones go?
By calling it pi 1 and pi 2 here, we are saying that those 2 bonds are equivalent to each other. And, number 1, they don't interact with each other. They are independent pi bonds. Said another way, there is no conjugation between them. Said another way, there's no resonance. Is there resonance possibilities for that molecule? Could I take these pi electrons and move them there? Yes, I can. It does generate a charge, but I have a resonance possibility here. What does that mean? Those 2 pi bonds are not independent of each other. They are coexisting, which means when we look at the molecular orbital diagram, they must all be interacting with each other, not 2 independent pictures. The end result is we get the diagram being shown to the right. I'm just going to erase all that. Okay? We would get a pi bonding interaction. We would get another pi bonding interaction. They would be slightly higher in energy. We get a pi anti-bonding and another pi anti-bonding. That could be hard to differentiate them, so we could call this pi 1, 2, 3, and 4. We get 4 molecular orbitals for this. How do we know what electrons to go into it? How many pi bonds? Electrons. How many electrons went into our pi system? 4. So I could now draw in my 4 electrons. 1, 2, 3, 4. What happens to the gap between those?
It's a big difference in energy.
It is a big difference, but in comparison to them being separated pi systems, if they are independent, that gap is larger. It gets smaller when we have the pi systems overlap. Why does that become important? Smaller, the electrons can jump easier, which means they need less energy, which means, right idea, keep going with it. Less energy would mean a larger wavelength, which would mean it would move from the ultraviolet into the visible spectrum. So what we are seeing when we think about color, you think about all the colors you see, particularly on people's clothes, it's all due to an organic molecule. An organic molecule that is absorbing all other wavelengths of light. Okay? And you're now seeing that light reflected on. Okay? What we can do is quantify that in UVvis. We put the dye molecule into our detector, and we just scan the wavelengths until we see where it absorbs. In this case, this is absorbing deep into the UV. What's it talking about? The gap between the HOMO and the LUMO. That was a lot, right? You're like, no, that was easy. That shouldn't have been easy. Okay, maybe it was too easy. Okay, that's fine. No one's shaking their head. As you increase conjugation, the gap between the HOMO and the LUMO decreases. So here we go. 1 pi bond, there's our gap. 2 pi bonds, because our energy doesn't get much higher or lower, the gap shrinks a little bit. What does that mean? This compound with that extra pi bond that is conjugated absorbs to a slightly larger wavelength. What happens when I add another pi bond? The gap gets even smaller. A smaller gap means less energy, which means
Stays in UV.
larger wavelengths. Larger wavelengths are visible. Okay, we actually move out of the UV. We move into the visible range. Okay, we've got that inverse relationship between energy and wavelength, and that messes with this a lot. Okay, so the biggest thing that you need to pick up is that when you increase resonance in a molecule, the HOMO-LUMO gap shrinks, increasing your wavelength. Should we say that again? Okay. The more resonance or increase in resonance decreases the HOMO-LUMO gap, which shrinks the energy, and it increases wavelength. Okay. I remember those of you like freaking out at this. That was literally UVvis. What I just said in 5 seconds, twice. That's what you're responsible for. It was a slow 5 seconds? 10 seconds then. So we can still see this experimentally. Let's go ahead and take a look at our ethene. There it is at 161. Okay, there's the Lambda Max. What happens when I add a bunch more carbons? It changed, right? Did it change much? 161 to 171 versus 455. Did it change much? No. So just adding sigma bonds doesn't really do anything. Why not? Sigma bonds aren't significantly changing your molecular orbital backbone on which this is based. Okay? What happens when I add a second pi bond? Because of course that should make a big jump. It was a tiny jump. Why was it so tiny? We just said the more pi bonds. We didn't say the more pi bonds. We said the more resonance, the more conjugation. There's one where we've added a second pi bond and it's conjugated. It has resonance. What happened to the wave numbers or wavelength? It increased drastically. Okay? So that's what you're keying off of. That more resonance, the larger the wave numbers. If we drop all the way down to the bottom structure, beta-carotene, your wavelength is now 455. You're actually into the visible light spectrum. Okay? Which is useful, because when do you use beta-carotene? Retinol? Okay. It's okay. Beta-carotene, the wives tell you eat carrots, you can see better at night. No one ever heard that? Yeah, there you go. Okay, beta-carotene is a molecule, okay, that can be used to make the molecules that respond to light. Why? They absorb in the visible range. Okay? When they absorb that energy, what happens to the pi backbone? So let's look at a simple case. Let's just look at the beta structure, the butadiene. It had 4 electrons. What happens when I absorb UV light? I eject an electron and it jumps up in energy, right? By jumping up in energy, what has now happened to that pi bond? I've broken it. If the pi bond's broken, what can it do? It could freely rotate. That rotation is what we use, or our brain encodes, as color and light that we turn into sight. It is the rotation of that double bond. That's what's happening. That's kind of cool. Whatever. Freaking biologists.
Okay, 2 questions. So this conjugation, is that just another word for resonance?
Yes.
Okay, second question. Why, like look.
Actually, sorry, I want to interrupt you, sorry. To make it sure it made it into the recording. Conjugation is just another word for resonance.
Okay.
It's just another descriptor. Yes.
So cyclohexene has 1 pi bond,
Mm-hmm.
but the one above that has 2, but one is.
So what caused that difference, you think? The ring. Okay? That ring is now changing the characteristics of that absorption pattern. Because it changes the absorption, we do see that change. How much did it change? Look at our differences. Okay? It really isn't all that different between all of those. You're still looking 20 nanometers. When you add a second pi bond, that's when you see a big jump. Okay? So the ring does affect the characteristics of that pi bond, okay? But it's still a relatively minimal effect. The big effect that you should be looking at is those conjugations. Okay? And if for any reason you wanted to study UV-vis spectroscopy, that's awesome. You'd be digging a lot more into that specifics of that. But if you don't want to, that's fine. I don't want to either.
What's going on with the hex 1
What's happening with the hex 1 ion? It's an interesting question. Notice its wave numbers didn't go up a whole lot either. But aren't there 2 pi bonds? Okay. Is there resonance? No. So why is it not going up a whole lot? There's no conjugation. It's the conjugation of those pi bonds that matters. Okay? So you really have to look for that resonance. Okay? Other questions? Okay, so only 10 more slides to go. So where do you guys have questions, or do you want me to just keep hitting you with these? This is exactly where you were going? Yeah? What are we looking at? This is our carbon NMR or CNMR. How do we know that? Look for that large range out to the 200. What do we see? 4 unique carbons.
3 alkanes. Question.
I think that's too low to be aromatic. I think you're getting a bit over 100 for that.
100.
Okay. So that's just questionable. Okay. I did hear someone shout out solvent, which would be an awesome guess if this was a real spectra. Not a real spectra. Okay. So if you're looking at the spectra packet, the last, I think, 3, A, B, C, are real spectra. I don't have mass specs for those, so I attempted to give you masses. Nobody's ever bothered to look at those until this semester, and some jackhole found that I've probably goofed the mass given to you, at least for C. And by jackhole, it was a good job. You should have noted that, so that's good. Just for the record. Okay? So be aware of that. So that's what I would expect for carbon NMR. When you look at the practice exam, okay, there is a full solve. There will be a full solve on this exam too. There's 4 spectra and then the structure. So I believe it goes 8 points and then 2. 2 points per spectra analysis. That's 2 points. How long did it take us to do that? Okay, that should be exceptionally fast. Okay.
Can we bring one of those papers, the sheets?
Nope.
Or we just memorize?
You got to memorize that. Okay. The point of memorization is to speed your solving process. You will already be crunched for time. Having it a sheet to reference is only going to slow you down. Okay? You need to have that practice with you. Okay? Particularly with spectroscopy, I find people that use the sheets do a lot worse. A lot worse. Okay. Is there a hand? Sorry. Okay, what do we have? How do we know it's mass spec? It looks nasty, okay. M to Z, we're seeing our numbers increase to the right. I don't think any of our other spectra do that. Okay, so now what do we have?
Mass of 110.
Okay, we find the tallest peak furthest to the right. Depending on how good your eyesight is, you could point all the way down to that stupid little thing. Actually, yeah. So, for really good eyesight, you might see that. Okay, and so people looking at it being like, what the hell? This is where I try to be nice. And what do I add over the top of this?
110.
So I have to figure out where my peaks are. Eight, 7. I thought it was 67.
Yeah.
Okay, so you should fully expect to see those numbers floating over there. So if you're like, but I got good eyesight and I see this thing, that's good for you. I'm giving you a hint. Either choose to use it or run down a rabbit hole. Does that make sense? Okay, so what does that hint tell you?
There's no bromine, no chlorine.
Before we get into bromine and chlorine, or nitrogen. Nothing to do with a lot. Easier. Grams per mole. Okay, what we're trying to do is identify our M+. Tallest peak, furthest to the right, 110. That's our molecular weight. So 110 grams per mole. Now that we have that identified, now what can you do?
No nitrogen.
No nitrogen because not odd.
No bromine, no chlorine.
No bromine. Why?
There's no second peak.
Okay, we need an M+2, 1 to 1. No chlorine.
Let's just be 3.
Same deal, M+2, it should officially be 3 to 1, just for the record. No iodine because
Not nice.
it's a small number. Okay, now what?
Start dividing.
Now we could start dividing by 12.
That's where you shine.
Someone help me out. 9, thank you. What? Oh, I see what you're saying, because it's 108. 2. So what does that mean?
Probably not.
We could have C12,
H2.
H2.
I like it. Perfect.
Okay, why is that not a good formula? That could absolutely work. I guarantee it. Triple bonds, rings, double bonds, up the freaking yin-yang. Yes, could absolutely be possible. Is that likely? No. So this should be eliminated as it is unlikely to have that few hydrogens. So what could we do? Subtract a 12, add a 12, and by subtract 12, subtract 1. And we would get C11H14.
Better.
Yeah, that's it's C9. C8H. So that's why you didn't do that.
That's why I don't like mass spec. Which is going to open us all up for the next fun one too, because we're going to have to bring up this stupid formula too. All right, C8H14. Are we better now?
Yeah.
Okay, thank you for catching that. Okay, C9, whatever. So C9H2 still was unlikely. It was just extra unlikely now. Okay, now C8H14, that makes a little bit more sense, right? Okay. So where could we move from that? So that's a possible. Could we do anything else with that formula?
Degrees of unsaturation.
We can do the degrees of unsaturation.
No, the formula.
What do you mean no?
We don't have to do it.
When we get the formula?
You need to understand your degrees of unsaturation. Yes. Right. So
It's 2 times C.
CnH2n plus 2. And I already screwed this up.
Minus.
2 degrees of unsaturation.
There.
Did I goof the math? Why did I divide by 2? Why did I divide by 2? So one option is saying it's the formula. That's actually not why I did it.
What? Oh, it is.
It is the formula. To make a degree of unsaturation, what is a degree of unsaturation? A ring or a pi bond. How do I make a pi bond in this structure? What would I have to do? Why did I divide by 2? For every ring or pi bond, you have to remove 2 hydrogens. That's why I divided by 2. So 4 was the number of hydrogens that made up that difference. I needed 2 per, so I got 2 degrees of unsaturation. Okay. For those of you being like, isn't there a formula to do that? That seems really bass-backwards and long. It is. You're right. There is a formula. I haven't memorized it. I have to do this. Okay? Because I'm so excited about calculating degrees of unsaturation. Okay? So, but that gives me a bit of useful information that I could find somewhere else, which is why I think it's a waste of time. But if you were forced into that bucket where you have to analyze it, then you've got to do it. Then you've got to come up with some way to do it. The way I do it is I pick the simplest molecule, say, how do I make that unsaturated? What does that mean? What do I have to do to derive that? I effectively derived the unsaturation formula in its simplest form. Okay? So what does that mean? With 2 degrees of unsaturation, what can I expect to find in my structure?
2 pi bonds, 5 bond R ring.
2 pi bonds, 2 rings, or a pi bond and a ring. Okay? All 3 of those are possible options. For those being like, well, that's like 3 choices. Doesn't that suck? Yeah, it does. This is why I think it's dumb. Right? But again, it's if you're forced into that bucket, that's what you got to do.
But you won't grade us on that, right? Like we don't do for everything.
I will not grade you on degrees of unsaturation for a full solve.
Oh, okay. Keyword.
Yes, that was very carefully phrased.
Okay.
So.
What about gaining additional points by having that as part of your solve? Since it's a stepwise.
It's only 2
grading
points.
process.
It's only 2 points. If you had it there and butchered something else, maybe I'd give you a half a point.
Mhm.
But yeah, each of those spectra in the full solve are only 2 points. So
So if it was 30 rings, would that be 30 pi, 30 rings, 2 pi?
so if it was 3 degrees, what are your possible options?
So you could have 2.
You're going to get a lot more options because you could have 3 pi bonds or 3 rings or 2 pi bonds and a ring, 2 rings and a pi bond.
That's just one more option.
Yeah.
Yeah, I think you're right. Yeah, that was only one more. Just you wait. Wednesday's coming.
Oh, don't start using that.
I take it back.
So, are we good with mass spec? So there's lots of stuff in there, and I'll also kind of give this as a pseudo plug for mass spec. We aren't even touching the surface of the amount of information that's in mass spec. Okay? Because we could look at that 81, we could look at that 67, we could look at all of those fragmentations to come up with ways to predict that. Okay?
You don't want us to write like no for old stuff, right? Or like to show our work?
That's an interesting question.
Just put no DS.
Yeah, you don't have to do that.
Okay.
Yeah. So for this one, God, there's a lot of stuff up there, isn't there? If you had just provided that for the show your work, yes. Okay, and for that matter, if you had just shown that for the mass spec, that would be full points. If your final answer was right, you could probably show that for the mass spec. Make sense?
It's gonna be your ring.
How many multiple choices?
There are 37. 38? 37 or 38.
Wait, so is that less short answers than last time? Or it's about the same?
It is actually shorter than the last exam, I believe.
God,
Yeah. So the way I timed it out, since you guys are asking about it, is the full solve, I said 10 minutes. So I said you should be able to do a full solve in 10 minutes. And yes, you should be able to do that. Okay. Particularly because you know 10 possible things, arguably 6 possible things it could be. So if you do all those 6, you're really just regurgitating what you've memorized. Okay, for the full solves. To start, yes. So on the exam, I allotted 10 minutes to do that, which means you've got 65 minutes to complete the rest of it, which came in at 40 questions for multiple choice. And then I can't count, so I'm at 37. I've already sent it off to be printed. I'm not dealing with it again.
I'll go.
And this time around, after I wrote it, 24 hours later, I went through and actually took it on my own to try and catch typos better than I did last time. I didn't actually find any typos, so I'm a little nervous.
Did you time it?
Oh, I didn't time it, and I didn't actually think to check actual score, but I got them all right. So,
Except for the math.
so except for the math ones. Technically, I didn't show work for any of that. What are we looking at now? Something ugly. HNMR. 3 unique hydrogens.
Alkanes.
They're all alkanes. Those people being like, dang, your handwriting sucks, that's good enough handwriting to get you points. So,
I can't tell them.
fair trades. Okay, so this is an interesting question that just came up. Okay, I can't tell how many peaks there are. If you can't tell how many peaks there are, what should you do? Ask. Okay, you should absolutely ask. Okay. I would like to say I'm 100% positive on it, but I can't guarantee that I actually went through and I made sure to hand draw them so you could actually see them cleaner. Okay, so in this case, we've got 1, 2, 3. I'm going to do that one in the middle here in a second. 1, 2, 3. And then we got 1, 2, 3. I don't think I'm making this easier to see. That middle one, short, taller, taller. Does that make it easier to see? Okay. One of the things that's challenging here is we don't have the integrations. I do give you the integration, so I'll just go ahead and throw some numbers up here. I do also give you, when it comes to HNM or the full solve, the back of the very first page is the spec.org file. I would encourage you to use that for the full solve. It is not required, it is just encouraged to use, okay? Because it will help guarantee that you've specified everything you need. So, what do we see?
First peak.
First peak doesn't help me out.
The one on the right.
Far right, over here,
Yeah. 3 peaks.
okay. We're looking at alkane, so we know there's a hydrogen bonded to a carbon because of that chemical shift. The integration says it's 3, which means we need to have 3 hydrogens on there, and we have 1 dangling bond. What does the next one show?
It's another CH, but S2.
It's a CH2. Okay. I haven't actually looked at neighbors yet, so we're going to ignore that for a second. Last one,
Another CH2.
because of the alkane range, it's a little bit high. It's starting to clear that too, so it might be dodgy calling it a carbon, but it probably is a carbon.
We know there's no.
Okay, so we've got those three as potential pieces. We could now start to try and jam those together, right, if we so chose, depending on what other information we had at hand. Ideally, we would take this a step further and look at the multiplicity. So peak furthest to the right has how many peaks? 3, which means
2 neighbors. It's carbon.
3 peaks, 2 neighbors. We have a CH2. Yeah? How about the middle one?
6 peaks with 5 neighbors. So it says
I got
CH3,
6
one
peaks.
is CH2.
So 6 peaks equals 5 neighbors.
CH3 and CH2.
A CH3, a CH2. It's going to be the only way we can break that one down. Last one,
2 neighbors.
3 peaks. The easiest way to do that would just be a CH2 next to it. Yep. Make sense? We could now try to connect things out. Anybody see anything? Okay. Probably looking at a CH3 bonded to a CH2 bonded to a CH2. Okay. This CH3 was the one about 0.9. The next one's about 1.5. The next one is at about 2.1. Anybody see a problem with this as a final answer?
It's not complete.
We're still missing that last bond on what it's connected to. The HNMR doesn't give us that information. What would we need to help figure the rest of that out?
Carbon formals or mass spec.
We'd have to look to the rest of our spectra. Our mass spec, okay, our IR, our carbon NMR, and see what other information was in there. Does that make sense? Questions? Okay. Last question for you. You have to finish this structure. This is all the data you're given. You have to finish this.
No, there's 2 double bonds. And there's probably some two.
How do we finish this?
On our grid.
Another CH3. Would that CH3 be the same as this one?
Yeah.
Yeah. Would these be the same as each other?
Yeah.
How many signals do you have?
2.
2. How many signals are you supposed to have?
4.
3. So that was a bad idea. Nope, you have to solve it.
An oxygen or a nitrogen?
Why do you want to put an oxygen or a nitrogen in there?
You wouldn't see any other hydrogen cluster?
We wouldn't see splitting. Okay, I fully accept that. That oxygen also adds a benefit because what would it do to those hydrogens?
Push the bond range.
It would cause them to shift. That one's shifted a little bit, right? So maybe. How many bonds should oxygen have?
2.
What's out here?
H.
If you put an H, what do you now have? You have a hydrogen which should show up as a signal, which means
It's probably the same.
it still doesn't work. Is this CH3 the same as that one?
Yeah.
Yep. Is this one the same as that one? Is this one the same as that one? How many signals do we have? 3. Do we maintain the ratio? Yep. That could work. Okay. Who's really good or is confident in their chemical shifts when it comes to hydrogen NMR? You could say no, that's fine. Yeah? What happens when you bond that oxygen next to that carbon? What happens to those red hydrogens? Where do they show up? They show up about 4. We're not at 4, which means it's not oxygen in the middle. Could it just be a straight CH2 across? That still fits all of our patterns, except that red one, would that shift above 2?
Wait, which red one?
There's only one that's red that's circled. They're both the same.
Wow.
No, it's one of the alkanes.
it would still be alkanes. It would probably show up under 2. So we have to add something in the middle to explain that chemical shift.
So nitrogen.
Nitrogen, how many bonds does nitrogen need? 3. What's connected to that last bond? Hydrogen. We'd have another hydrogen in our spectra. Can't put that in. We could throw on another carbon. What was your chemical shift range? If oxygen causes it to shift to 4, guess what nitrogen does? 3.5. Okay, so I like it, but didn't work. Halogen. What's the problem with a halogen? They can't have more than 1 bond, so that doesn't work.
Just get it wrong.
Throw in another carbon. We don't have any information about the carbon anymore. I'm allowed to throw in another carbon. I just have to make sure that that carbon is not connected to a hydrogen. So I could throw it up to a double bond to an oxygen. Guess where the red hydrogens shift when connected to a carbonyl? 2.1. Where's that signal showing up? 2.1. That's likely the structure that created that. Okay? Beyond what I'm asking you to do. Okay? I just said you're now forced to. Make sense?
Yep.
Cool. Study. Do well. Please. 40 hours?